On Tuesday, we stopped by an example which I asked you to please do it at home. And the example was checking about if these matrices are positive definite or positive semi-definite or none. The first one was this. So is this one positive definite? Did anyone try? How could I understand if this one is positive definite or positive semi-definite or not? What was the definition? You remember, Nastia? No. It was A should be symmetric, which means that A is equal to A transpose, which in case it is. And then for symmetric A, we were defining the positive definite to be if X transpose AX is greater 0, X transpose AX is equal to 0. It is equal to 0 if X is 0, otherwise it is always greater than 0. So we have to check this one. So how do we check it? We understand that X, we define X to be a vector of 2 by 1. Then from here, X transpose is the row vector of x1, x2 multiplied by A, multiplied by X itself, which is x1, x2. It will be, this is 1 by 2, 2 by 2, 1 by 2, 2 by 1, 1 by 1. So we have one expression. If we multiply, we will get this expression. 3x plus 3x1 plus 2x2 square plus x2 square. Now, question. We got this expression. Just wait for a second. I'll let you write. We do this multiplication. We have an expression after this. Now we have to look at this expression and see that if x is not 0, do we get always a positive answer? If x is not 0, which means x1 and x2 are not 0, do we get positive results? Yes. Always, because this is always greater or equal than 0, this is always greater and equal than 0, because they are not 0, we know that the result is greater than 0 if x is not 0. What will happen if x is 0?
0.
The only 0 will happen with a positive number plus a positive number, and it has to be 0. The only two non-negative numbers which we add down, we get 0 is at 0. And we know that this is 0 if and only if x is equal to 0. So it is that this matrix is positive definite. Now we have another matrix, let's call it B, which is 9, 6, 6, 4. And we want to see if it is positive definite or positive semi-definite. What was the definition of semi-definite, by the way? Positive semi-definite, we have the equality also in here. In other words, if x is not 0, we should be positive or 0. And if it's 0, we definitely are 0. So the red part means that we have to add this one. Now let's check. Let's check. Again, we define x to be x1, x2. And if you make x transpose bx, you will get this expression. 3x1 plus 2x2 squared. We can check it. One question. Suman. What about this one? What can we say about this? Is it always greater than 0?
Not always. If one is to be 0, then it is 0.
So is it always greater or equal than 0?
Yes.
It is always greater or equal than 0, so it's always positive, no problem. So this is greater than 0. We have to check about the equality. But before that, can you tell me that what is x transpose bx if x is equal to 0? I put x on 0, it means this is this, 0, 0. I put it in here. What is the result? 0. Now, question. If x is not 0, do I get this expression to be equal to 0? In other words, is it greater than 0 or is it greater or equal than 0? This is greater equal than 0 because for x equal to, let's say, -2 and 3, which is not 0, -2 multiplied by this is -6 plus 6, it is 0, so the result is 0. So we see that here d is is positive semi-definite. Because we find an x who result into 0, but it is not 0 itself. If the result would be negative, then it's not positive, definite or positive semi-definite at all. Now, today we will start a new section which is about projection and inner products and norm of vector and matrix. And it plays a very important role. And you can see them actually quite a lot in many computer science applications. And if you are working on optimization, some of the terms that today we will learn should be very familiar with you because they are being used in optimization also quite a lot. So let's define projection. The mathematical notations that we use for projection, as the book states, is in this one. Let V be a vector space with this property. What was this notation? Direct sum, which V is the direct sum of two other vector spaces, okay? So every V belonging to vector space V has a unique decomposition of V is equal to x plus y with x belonging to vector space x and y belonging to vector space y. So we define the projection of x and y of V in this form, that V goes to x, which is a subset of V. And this is called projection on X along Y. And this is how in abstract mathematics they define it. In daily life, we define it this form. I can write any vector of V as the combination of two terms in different other vector spaces. Any vector in Cartesian, in 2D Cartesian, can be written as combination of i's and j's, right? Any vector that you pick up, you can write it as mi plus nj. So this is the general form that we have. Geometrically, it means that our vector V can be decomposed this vector space V, this vector space X, this vector space Y. So it can be decomposed as addition of the vector X and vector Y. Now, our projection is linear and has this property that P squared is equal to P itself. So today we will look at the theorems and properties that we have over this projection. We know that projection is very important. In the pattern recognition, for instance, you know that we are using it in order to do, let's say, clustering, or in order to extract some features. And there is actually a theorem regarding this comment, and the theorem says that a linear transformation P is a projection if and only if it is idempotent. Idempotent means that P squared is equal to P. And P is a projection. We understand that P is a vector, N is a matrix. If and only if I minus P is a projection as well. As a matter of fact, even that means P squared is equal to P. Projection on Y in line with X is I minus projection on X in line with the Y. This is a general form for any X and Y. In case that Y is orthogonal complement of X, then P X and X orthogonal is called orthogonal projection. Like Cartesian coordinates that we have.
If you don't press it down, just lift it up to slide down. So you press it down
okay.
at the start and then arrange.
Let's have another theorem. If P is a matrix of n by n in R, and is an orthogonal projection, so it's this matrix orthogonal projection if and only if not only is that idempotent, but also the result is equal to P transpose. The proofs of these theorems are actually available in book cited by some other previous theorem that we have. We are not responsible for those theorems. We will soon use all of these theorems in some examples of application. Do you remember the four fundamental subvector space that we had? Do you remember them? We have four fundamental subspace. What are they? RA orthogonal, null space orthogonal. And if you remember, we had difficulty of finding out till we had the SVD. And SVD helped us that we can look at the U1, V1, and accordingly say that which one is null space, which one is null space orthogonal, and which is R, and which one is orthogonal. Now, we want to see the same thing on the projection, and we want, because now we know SVD is our friend, and we can use it in order to calculate it. Let A be in R n by n, and rank R. Then we know that A can be written as U sigma V transpose, and also it can be written as U1 S V1 transpose. What is the size of U1? What is the size of U? What is the property of U1V? There are two properties they have. We said they are, they are orthogonal, and they are S squared. They are S squared matrices. So can you tell me what is the size of U now? M by n, and this one is n by n. And this, we know that always is the same as the size of the matrix. Now, what about the U1? What is the size of U1? We understand that it is m by something, and this one is also V transpose is multiplied by n. So it should be n multiplied by something itself without transpose. Why? Because as a result, this should be m by n. But what about the terms that we have in here? What is the size of this?
1.
No. It is R This is R by R. This is actually N by R, but with the transpose it will be R by N. What is R? The rank. If you remember, we could write it, we could shrink it based on the rank, and you can ignore all those singular values which are 0. So if we have this, then the 4 fundamental orthogonal projections are P of RA, P of RA orthogonal, P of NA, P of NA orthogonal. This one is A plus. This one is A plus A. This means U1 transpose. This one means V1 transpose. This is, you know that they shouldn't have any intersection. So do you know what it is? It is I minus this term. And this one is I minus the other term. This will be U2 transpose. This will be V2 transpose. So if I know the SUV of A, I can easily see not only the RAs and NAs, I can always calculate the fundamental projection of those vectors. Let's do an example. This is at determine the orthogonal projection of a vector V belongs to Rn on another non-zero vector that belongs to R n. We want to project one vector on another vector. Think of the vector W as an element of the one-dimensional subspace of our W. So we want to calculate P of our W and V. Basically, you have to calculate W plus V. Do you remember what is the W plus? We had it in our book. For a vector, it's defined as W transpose divided by W transpose multiplied by W. So we can write that W transpose V divided by W transpose W multiplied by W. Now, we can find a vector, let's say Z, which is orthogonal to W. So that the vector V can be written as PV plus Z. Let's visualize it in this form. I have W and I have V. I have find the projection of V on W. What is this one? PV, right? It says that there is an element also, I can define it Z, which can be like this, can be my x-axis, now this can be my y-axis, isn't it? And any vector can be written as its component plus the y component. So this is what it says. Now, what I want to do, I want to find a value for Z. Because if I want to decompose it, I need to find a value for Z, right? So what is the value for Z? Okay, can you guess what can be the value for Z? It will be V minus PV, right? Because if instead of Z I put V minus PV, PV's will cancel each other and we will have V. Which is 1 minus, well, I minus P multiplied by V. You remember that, what is I minus P? P of Y and X was I minus P of X and Y. So we got to the point. Which is equal to V minus, actually V transpose V over V W transpose W over W. I just substitute for P. Right. How do I know that W and Z are orthogonal? Proof or show that W and Z are orthogonal. What is the meaning of orthogonal? How can I understand two vectors are orthogonal? Right? This is the meaning. Okay, proving. Look, W transpose Z is equal to W transpose, what is Z? V minus W transpose V divided by W transpose W multiplied by W, which is equal to W transpose V minus W transpose V divided by W transpose W multiplied by W transpose W. W transpose V minus W transpose V is 0. I write the notes, then I write the numerical example, and I want you to do that numerical example. Let x belongs to R n in any arbitrary vector. Then any arbitrary vector in Rn can be written as this decomposition. Do you remember what is P and orthogonal? Look at the formula that are written. P N A orthogonal. It is come on, what was it? Less we have written. It is A plus A, right? The other one is I minus A plus A. But what was it? A plus A is V1 transpose X. What is I minus A plus A? V2 transpose X. Do you remember what was VV transpose? VV transpose. In SVD, V multiplied by V transpose is equal to?
I.
Yeah, I. Because they are orthogonal, we know that. Now let's see where we can use these formulas in a numerical example. Let for A, which is 1, 1, 0, 0, A plus to be 1 over 4, 1 over 4, 0, 1 over 4, 1 over 4, 0. Decompose the vector 2, 3, 4 transpose, so it means that it's a column vector, uniquely into the sum of vector and a vector in NA orthogonal and a vector in NA. In other words, decompose my vector x into P N A orthogonal x plus P N A x. How can we do this? No, how can we do that? What is the solution of this example? I mean, not the number wise, what is the solution? the solution, isn't it this? A plus A multiplied by my x, this is my x, plus I minus A plus A multiplied by x. What is A? What is A plus? Just put it there, multiply them, and we multiply by x. And if you do, you get the result to be 5 over 2, 0, plus minus 1 over 2, 1 over 2, and 4. So this is a projection or NA, orthogonal, this is a projection or NA. It's like this. It says that I give you a vector, can you please tell me what is the x? What is the x component? What are the y components? We know that they are orthogonal to each other at any direction. Now, let's define the inner product. We are familiar with the inner product. What is the easiest name that we know for the inner product? Dot product. So, we have to see some theorem, some general form, which on a special case, it will be our dot product. Let V be a vector space over real numbers R. Then this notation goes to R is a real inner product if, so this notation that we have, like let's say vector x and vector y is inner product if there are three conditions. First one, inner product of x by x is always greater or equal than 0 for all x belonging to V. And apparently x, the inner product of x by x is equal to 0 if and only if x itself is equal to 0. If you are talking about R, we are talking about real inner product, x inner product with y is equal to y inner product with x. And the third one, x inner product with alpha 1 y1 plus, or alpha y1 plus beta y2 is alpha inner product of x and y1 plus beta inner product of x y2 for all x y1 and y2 belonging to V and alpha and beta belonging to, of course, R. So we understand, as we are defining it for R, we can define it also for C, complex. We should do it in 3 minutes. From chapter 1, chapter 2, and even before in undergraduate level, we are very familiar with this. Let V be Rn, then we know that x and y inner product is actually x transpose multiplied by y. And is known as Euclidean or we call it dot product. So dot product was the inner product for over Rn, whereas the general terms are defined that way. Let V be Rn, then the inner product of x and y be q. Have you seen this notation? It is x transpose qy is called weighted inner product. It's called weighted inner product, where Q is equal to Q transpose and it is positive definite. In line with these ones, we can always say that if A belongs to R n by n, then there exists an A transpose belonging to R n by m. There exists a unique linear transform of A transpose which belongs to Rn by m, such that x A y is equal to A transpose x and y. And there exists a hash called weighted transpose, so that x A y, the weight of q, is A hash x y there is q. Do we know how to calculate A transpose? Is there anyone in this room who doesn't know how to calculate A transpose? You know, rows goes to the columns, right? Sam? You know how to calculate transpose. What about the A weighted transpose? How can we calculate A weighted transpose? What is this? X A Y. It means it's X transpose Q A Y, and this one is A hash X transpose Q Y. Sorry, this should not be Q. We should change the weight. The weights will be changed. which is X transpose A hash transpose R Y. So by comparison, we understand what should be the A hash will be R inverse A transpose Q. You know, these terms, they have to be equal to each other, right? So what happens is this: A hash transpose R is equal to Q A. I transpose both sides. I get A transpose Q transpose. What is Q transpose? What is Q transpose? I erase it. Q transpose is Q itself. So it will be R A hash is equal to A transpose Q. So A hash is R inverse A transpose Q. So as we have the weighted transpose, we can now define two vectors X and Y are called Q orthogonal if, what is the definition? What do you think the definition will be? The inner product with respect to Q is equal to, which is X transpose Q, Y is equal to 0. X and Y are orthogonal if X transpose Y is equal to 0, and it will be called Q orthogonal with respect to Q if we have the inner product with respect to Q to be 0.